Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its products and experiences in transport and logistics. This video is confidential and may not circulate outside the receiving company without HI's authorization. This video is confidential and may not circulate outside the receiving company without HI's authorization. Artificial hypothalamus. The power of today's technology is not in the mathematical calculations that it allows to perform, it is in the mathematical calculations that we can imagine that we can perform. Complex transport and logistics systems optimization. The table presents the models developed by HI for trucks transport optimization. Urban routing optimization. Challenge: to implement mathematical models for urban routing operations as a logistic operator. Solution: design and implementation of routing models for trucks in urban space that include the allocation of the orders to be delivered, which is handled at the level of the boxes that contain the products. Result: deliver the models to the client who implemented the models in its information technologies system. Regional routing optimization. Challenge: to implement a DSS to management the routing of truck and van type trailers for two types of transport services. General cargo: any type of cargo of different nature that is transported together, in small quantities, and bulk cargo, transported in a massive, homogeneous way, without packaging, whose usual handling should be carried out in special vehicles. Solution: design and implementation of a set of mathematical models to define routes of client services, and assign trucks and van type trailers to routes. The models include single trucks and empty trailer movements, to coordinate services across multiple regional offices where goods are delivered and or loaded. Result: the optimization models coordinate a transport fleet of more than 400 trucks, 400 trailers, 200 tanks, 500 drivers, and relationships with more than 2,000 other transporters. Vehicles routing and cash transport. Challenge: to implement an informatic tools to optimize its collection and distribution operations of cash and securities. Solution: design and implementation of a set of mathematical models to define routes of client services, assign vehicles to routes, and assign crews to vehicles. Result: deliver the models to the client who implemented the models in its information technologies system. Cash transport vehicles routing models interconnectivity. The implemented solution involves the coordination of multiple models, each with a specific function, since it is not practical, nor viable, to think in a single model that does everything. Under the concepts of HI, in practice it is in an artificial brain. Vehicles routing in mines. Challenge: to develop a routing and scheduling model for mines operations. Solution: design and implementation of a routing and scheduling model for mines operations. This includes mining areas, waste and extraction, equipment, shovels, trucks, workshops, gas stations and chemical composition, quality specification for blending. The model may consider the shotcrete application, the coating that is put to the rock once a gallery has been made in an underground mine. Result: use the mathematical model in a proof of concept for a mining company in Peru. Gasoline distribution optimization. Challenge: to implement mathematical models for urban routing operations for a third-part user. Solution: design and implementation of routing models for gas tankers in urban/rural space. It includes time windows service for each customer, limited number of loading racks in the load bays, inventory levels on tanks, and preparation time for change in product loaded. Result: the optimization model handles 250 orders daily average, 169 clients or nodes, 139 trucks, 7 loading bays, loading racks, 3 shifts. Solid waste transportation. Challenge: to implement a DSS for solid waste transportation. Solution: design and implementation a set of optimization models considering two main process, house by house, garbage covers, and containers. For optimal solid waste collection, the model defines I. Allocation of blocks to collection sectors, 2. determination of the number of visits per collection sector. 3. Allocation of operational resources to sectors. 4. Definition of optimal paths within each sector, and v. Planning routes, schedules and frequency of visit. Result: the model was delivered to a consulting firm. School bus routing. Challenge: to develop a routing model for collection and/or distribution as school students. Solution: design and implementation of a routing optimization model. Result: implementation of the model in a web server to be used as MOS, Mathematical Modeling as a Service. Distribution planning and propane gas gathering. Challenge: to implement mathematical models for distribution planning and propane gas gathering. Solution: design and implementation of a mathematical model for distribution planning and propane gas gathering. It is aimed at supporting the weekly and daily programming and operational rescheduling of trucks dispatch. The modeling hypotheses are as follows. Fleet of vehicles consisting of multiple type of trucks and multiple type of LPG trailers. Trucks can be moved with or without trailers. A truck can tow some type of LPG trailer. LPG trailers can be dispatched with or without charge. Vehicles move between nodes, or terminals. In the nodes there may be demands that must be met or purchases that enter LPG into the system. In the nodes there may be demands that must be met or purchases that enter LPG into the system, and LPG storage tanks may exist in the nodes. Result: the models were delivered to the client. Less than truckload revenue management optimization. Challenge: to develop a DSS to support LTL, less than truckload trucking, business of a transport broker. The central problem is to choose the most profitable transport service demands, for direct long-haul routes or for multiple pickup and delivery routes, and fix the offer price for requests for transport services or accepting an offer previously agreed in a long-term agreement. An LTL network is made up of a transport company with a fleet of trucks, which serves a sequence of delivery requests, received either by phone, mail, or internet. Solution: design a DSS for LTL revenue management that must have the following models. ML-like models are used. I. Demand winning bids determines SVMs, support vector machines, to segment winner bids of prices offers to charge to load generators. 2. Supply winning bids determines SVMs to segment winner bids of prices offers to pay to the transporters. 3. Link LTL network dispatch and revenue management including the SVMs that defines the winning frontiers for price offers. Result: proposal showed to potential client jointly. Less than truckload revenue management optimization. Challenge: to develop a DSS to support LTL, less than truckload trucking, business of a transport broker. The central problem is to choose the most profitable transport service demands, for direct long-haul routes or for multiple pickup and delivery routes, and fix the offer price for requests for transport services or accepting an offer previously agreed in a long-term agreement. An LTL network is made up of a transport company with a fleet of trucks, which serves a sequence of delivery requests, received either by phone, mail, or internet. Solution: design a DSS for LTL revenue management that must have the following models. ML-like models are used. I. Demand winning bids determines SVMs, support vector machines, to segment winner bids of prices offers to charge to load generators. 2. Supply winning bids determines SVMs to segment winner bids of prices offers to pay to the transporters. 3. Link LTL network dispatch and revenue management including the SVMs that defines the winning frontiers for price offers. Result: proposal showed to potential client jointly. Balanced food supply chain optimization. Challenge: to implement a system of mathematical models for balanced food supply. Solution: design and implementation of a DSS with the following optimization mathematical models. Production in the farms. Production in the factories, considering the age of the animals in the farm's trucks routing operations. Result: the system was developed as part of a high research and development process. High project, Real-time transport distributed optimization in metropolitan regions. Challenge, in Industry 4.0, new technologies, IoT and big data, changed traditional moment-based optimization for real-time event-based optimization, where the models will run autonomously, and distributed across multiple locations, when necessary, by events. Solution. It implies that each system agent, or component, needs to know what information it needs to take from the measurement systems, and what information it needs to provide for other agents to make their decisions, using asynchronous parallel optimization methodologies, to keep the end-to-end system on the path of optimality. In the case of freight transport, the process of planning transport operations in a metropolitan region could be carried out as follows. At a certain time, the central dispatcher, CD, plans the routes to fulfill the transportation services. This involves solving the VRP-TWTDTT problem, the vehicle routing problem with time windows and time-dependent travel time, optimizing a target function according to the company's business rules. This process would be carried out centrally to generate the route, sequence of customers, and the path, sequence of streets, for each vehicle to be used that day. Each route is uploaded to an intelligent mobile device in the vehicle, BC, through which measurements and information from a smart metering, SM, system are received, for example Waze, and during the route, at the end of the service on a client, the VC mobile device requests MS for information about estimated travel times and optimal routes to complete the trip. With the new information, the VC solves a TSP, travel salesman problem to recalculate the missing route, order and service times, and send that information to the CD, so that, if necessary, he can reorganize the planning of all routes. High project, real-time distributed optimization in regional transportation systems. Challenge, fuel consumption can account for up to 64% of the variable operating costs of a land transport fleet, therefore, it is a critical factor in truck route planning and scheduling. Solution. In state-of-the-art cargo haul trucks, the engines are electronic, digitally controlled, with near-environment telemetry capability and flexible in their operation, so the driver's skills have a major impact on engine performance, and therefore fuel efficiency. This autonomous capability of modern vehicles can be called optimal short-range control. However, the medium-term planning of operations is related to the entire truck journey. The importance of this planning can be seen in the engine performance curve, such as the one shown in the figure, where it is observed that operating in a range of 1,100 to 1,500 rpm obtains optimal fuel economy, but if operating between 1,500 and 1,800 rpm optimal power performance is obtained, with higher fuel consumption. The problem of optimizing energy consumption is complicated because the energy consumption function is nonlinear and depends on factors that are a result of the decision-making process, such as the load and the position of the truck. The factors that define fuel consumption can be divided into static, e.g., slope and roughness of the road, and dynamic depending on traffic and the weather conditions of the route. Although the mathematical problem is complex, the power of parallel computing, the effectiveness of optimization algorithms, and online databases, allow it to be solved according to the principles of autonomous real-time distributed optimization. Complex transport and logistics systems optimization. Multimodal transport. The table presents the models developed by HI for multimodal transport systems optimization. Port operations optimization. Challenge, to implement tactical planning and scheduling models to optimize its operations and commercial services. Solution, implementation of a set of optimization models for I, the definition of operations timetable, and 2, the allocation of ships to docks and cranes to ships, to optimize the management of shipping services, in the 2 terminals of the Port of Cartagena. Result, the mathematical models allowed to optimize operations of the port for I, planning terminal services assignments, 2, planning big events in the port, and 3, analysis of commercial opportunities. Routing boats in fishing transport systems. Challenge, to develop and implemented a model for planning and scheduling the allocation of fishing boats to process plants. Solution, design and implementation of a set of optimization models for planning and scheduling the allocation of fishing boats to process plants. The decisions supported by the models are Number of vessels to be departed daily. Fishing destination by vessel. Quantity forecasted, tons, of fishing per vessel. Assigned return plant per vessel including its scheduling, times, arrival, start downloading, finish downloading. Quantity forecasted of fish purchase from third parties per day. The modeling includes the vessel speed navigation, fish quality degradation as a function of the time on the vessel, and future fish flour blending considering inventories in the plants and the commercial commitments. Result: implementation made jointly with a fishing company, mainly engaged in the business of fishmeal. The fishing company operates, during the fishing season, 100 daily average boats, 8 ports, process plants, with 2 types of production technologies. Research and Development Project, Oil Transport by Sea, Planning and Scheduling. Challenge: to develop and implemented a model that supports the programming of collection and distribution operations of products, oil, coal, using different transport maritime modes, like tankers, barges, etc. Vessel speed optimization. When it is necessary to make decisions about the displacement of the vessel, it is of fundamental importance the correct modeling of the consumption of energy, which has a nonlinear behavior, with respect to the engine speed of the vessel. This constraint can be included in the mathematical model, as well as the modeling of tidal movements when entering or leaving ports. Result: implementation of the model using as a study case the oil products distribution between ports and refineries in the Peruvian coast. Assignment of locomotives in rail transport. Challenge: to automate the assignment of locomotives to already scheduled travel trains. Solution: design and implementation of an optimization model for the assignment of locomotives to travel trains, considering key characteristics of the operation of the system. The model allows adjustments to be made to the allocation of locomotives for regular trains and to generate new allocations in case of failed locomotives or extra trains. It executes the assignment process periodically, scheduled, manually, run the process at the user's request and by events, due to an eventual abnormal situation. Result: use the mathematical model in a proof of concept for a Mexican railway company that operates more than 8,500 kilometers of railways and connects 5 cities along the border with the United States, 4 ports in the Pacific and another in the Gulf of Mexico. This was a POC coordinated under a business partner agreement with a business partner. Project: real-time optimization of the operations in oil pipeline systems. Challenge: to design and implement models for real-time optimization of the operations in oil pipeline systems. Solution: design and implementation of a set of optimization mathematical models, that include the use of pumping stations, and the simulation of operating conditions, based on detailed models of the hydraulic behavior of the system components. The solution includes large-scale optimization methodologies. Result: real-time operations model to dispatch the batches of products, heavy crude oil, in the pipelines. In test case runs, it was verified that the difference between minimizing energy consumption and minimizing the total cost of operation can be of the order of 20%. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.